Hey, what's up, guys? It's been a while since I've done one of these, so bear with me. I don't get a chance to do these as often as I'd like. Um, I wanted to talk about a topic today: how to better cool your car. So, we recently went up. Actually, reminding me to do this is we recently went up with some buddies up in Angeles Crest. I'll post a little clip on there. And we, just had fun. It was starting to get hot. LA is starting to get warm here in the summer. And one of the Corvettes, stock Corvette, kind of basic rental Corvette, was overheating up at about 4,000 feet, 5,000 feet elevation. And I was just like, whoa, that's a, basically bone stock Corvette, kind of rental quality, which is, they should be pretty hardy, right? Or pretty beefy in terms of that kind of stuff. But we all know Corvettes have a problem. I just didn't realize the basic base model would have that. So anyway, thought about talking about a topic that may or may not help you, but it certainly helped me as I've researched this over the years, because in the NSX, cooling the NSX is always been an issue until we actually engineered. I helped engineer, or test rather. I wasn't an engineer. I'm not an engineer by any means, so all of these tips and tricks are just what I've learned personally and kind of test to. But if someone smarter like Jason from Engineering Explains, who by the way has some really cool videos that go more in depth about this topic than what I can do today, so be sure to check out his videos. I just wanted to go through some of the things that I think you should do or look at when you want to properly or better cool your car, because we, at least most of you guys watching this, I'm assuming are tuners or want to improve your car, mod it, update, make it faster, stronger, make it cool better, whatever. So just wanted to go through a few things that might help you guys out. I made a little list. Maybe this will help. Something to just talk about. So let's talk about basic radiator cooling capacity. Let's talk about air throughout the car and in and out of the radiator. Let's talk about water flow and the water pump itself. Let's talk about system pressures in terms of boiling point and basic pressure, gas pressure in the car or in the cooling system, and also of course proper coolant. So those are kind of the 5 things that I wanted to chat with you guys about today. And by the way, this video is sponsored by MASiV Radiators. Thank you guys for helping me out with our radiators and designing one for the NSX. And I'll show you guys kind of all the effort that has gone into the design process, and why it's kind of more a labor of love than it is of profit, to be honest. So over here, there's a bunch of things to consider when talking about radiators, right? And those things include the density of the fins, the fin pitch. So as the air strikes through and runs through the radiator, what kind of fin pitch does the fins have? And also, of course, the fin design itself. Is the fin just kind of straight through? And of course, there's also the tubing capacity. So the actual coolant water capacity in the tank itself. So it's important to note that one of the most important parts about radiator design too is the material. So whether it's aluminum, whether it's kind of this is an OEM NSX rad. I think it's got, I don't know, like 70,000 miles on it or something, maybe more. It's an old one I had. I just have it lying around as a spare in case I need to throw something in there pretty quickly. But this obviously has the plastic end tanks with the clamped on, I guess you'd call this a header design, and aluminum actual heat exchanger element itself with, I don't know, a bunch of tubes that I don't want to count, and where the fin density isn't quite as dense, but it's designed for a specific condition that, I don't know, something like 90% of the drivers of your average NSX would ever need. So for really high abuse on the track or really high usage on the track, this does overheat, at least here in California and Arizona. And for everyday driving on the streets, this cools really well. So with a basically quiet, low CFM fan. Okay, so one thing you guys got to understand too, and I think y'all probably know this, but when designing stuff for a car, it's always a compromise. The challenge for manufacturers is always to kind of make things good enough, because whether it be an engineering exercise, you don't want to, throw too much brain power at it because it's expensive, right? You don't want to throw like super exotic materials at it because it's expensive. You don't want to throw a lot of bulk into it because it weighs a lot. I mean, it's all sorts of stuff that will cause manufacturers to compromise in many areas depending on what they think is the biggest target audience for that particular vehicle. So I want to show you guys here a prototype of an early generation MASiV radiator that we were testing with, and this is like one of the early ones. You can see, I don't know if I can pull close up there, but the fin density is really very dense. So you can also see that the number of the number of tubes within it are maybe 3 or 4 times what's in an OEM setup. So this is also 100%, or I should say, it's a copper and brass design. So you have copper, which is about 30% more, I should say 30% better thermal efficiency than your typical aluminum. However, again, compromise, it's also a bit heavier. So there is no perfect material, I should say, but it's also going to be what is the most perfect material for your application. So this one, it cooled extremely well. However, it required a lot of airflow. So we decided to not put this into production because, or I should say MASiV did, because it was just, it was a bit too much, it was a bit too heavy, it was it required really strong fans for it to work, and a lot of airflow. So a ducted hood, a proper ducting underneath and into the radiator and over it. So this was an early prototype just to show you guys kind of the iterations. Then 2 or 3 prototypes later, maybe I can show you guys this. I just pulled this out of the box. This is a production version, which actually uses OEM style bleeder valve. So you'll take your factory Honda bleeder valve and stick it in there, because, as a side note, the ones we were using before, kind of your standard, many radiator companies use this. This kind of more or less this design was just over time it started to leak. So that was not a good solution, or at least it wasn't a good for longevity. So this one, sorry, it's backwards, but this one, you can see it's got kind of an in-between fin design. It's got an in-between density of the number of tube rows, and it's just kind of a better compromise that is proven to works great in really hot LA traffic with almost no airflow. And I have it now in my car, so it's been on my car for, I don't know, 3 or 4 years, and it's been working great. And basically, I don't know, I guess that's it about radiators, right? So you want to choose a radiator that is well tested for the car, because a lot of companies out there, and I think this is for cost issues, etc. And I won't ever fault a company for wanting to get costs down. I will fault them for trying to cheat a customer if they're charging a customer too much for the engineering that it took to produce it. So anyway, that's just my own personal thing. But there's a lot of good radiator companies out there. Obviously, there are some that are very popular. with the crowd, but we've tried a bunch of them, and the only ones that actually worked for me and a bunch of other guys who are actually racing their NSXs in very hot temperatures was this guy right here. Not only that, but it's 100% drop-in, so that was important to me, which is this unit over here. So what's next on the list? Airflow. Airflow is very important. Okay, so you can see on this car I actually have a duct or vented hood, but I've also got, I don't know if you can see down there, it's a full covered underbody kind of front belly pan, so there's no air. When air comes in through here, goes in through there, it has nowhere else to go but up and through the duct. So that's really important because I'll try to show you guys a better demonstration here. Whoa! So when air comes through and comes through down here, it comes to a little bit more of a high pressure. And the trick with air is you got to think about, as it goes through the radiator, it needs a place to escape, right? So as it escapes, it needs a low pressure area which it wants to naturally go through and out the vent. If you ever see in traffic, you'll see sometimes you get that heat warpage of the air. It's kind of like fizzly and like kind of like a bad trip. You can see it all come through here. It's actually interesting. So anyway, as the air rushes through here, it goes through the radiator and right up through the top. So an important part to, let me just, an important part to understand about the movement of air is air always wants to go to the low pressure area, right? So it's really important to create as much low pressure behind the radiator back here as possible. And it's also important to note that you can put really strong and powerful fans. Actually, notice I'm using the factory air shroud and also the factory fan here. All I did was I bypassed the, this is kind of ghetto, but I need to redo that. I bypassed the 2-speed resistor, so it's anytime it comes on, it's always running on high speed. Sorry, I'm kind of babbling now, but what's important to note is air always wants to go to a low pressure area. So one thing I have not done, which I really need to do and has been on my to-do list for like years, is build a proper duct that comes up here. But because I'm not happy with the tank on the lift system and I haven't cleaned up any of the wiring, I just haven't really gotten around to it. Then I need to get through, I was testing this bar, which actually I really like a lot. It's the only bar that connects actual true chassis points on each side, not like the one that Stimpo used to sell, which is a bit different down there, but I don't want to get into that right now. So back to the air. As you can see that I want to talk about kind of fans for a second, because the OEM design, kind of looking at it backwards here, there's actually space over here, maybe 2 or 3 inches on each side, 2 or 3 inches right there, that isn't covered by the duct itself. So that means that OEM engineers wanted free flow from the outside to come through here, and in the original NSX design, it would go under the car and out the back, or out the sides or out the back. So it's important to keep in mind that when you go with a shroud and a fan combination, that there are a few things to consider, right? When you get, like, say for example, a high power spall fan or some kind of aftermarket pusher or puller type. By the way, you want the puller type. Excuse me, I was waiting for that. It's important to note that a 3000 CFM fan, say at about 16 inches in diameter, I'll put there's actually a website that does a calculation for you if you don't want to do the math. I'll post it in the link. But let's say a 2,000 to 3,000 CFF fan going at full speed, 16 diameter fan. So something, something like this that pushes 3,000 CFM, which is a lot. It's a really high power fan. It's really noisy. It sounds like a turbine engine. I've tested a few of them. That will push air, or I should say pull air through here. It'll pull air through here at a speed of, at 2,000 CFM, will pull at about 16 miles an hour. And a 3,000 CFM will be about 25, 26 miles an hour. So what does that mean? It basically means that if this fan is going at full speed, then the air flowing through it is the same as the air flowing, or is the same as what your car will push naturally. Again, assuming that it's a free flow situation, right? Air pressure and all that stuff makes a big difference as this hood is closed. But let's just assume in a perfect world, it'll push air through at that 25 miles an hour or 16 miles an hour. So when this fan is fully on and running, right, it's running at super high speed, is drawing like, I don't know, 30 amps or something, and you're now going like 30 miles an hour or anything faster than 25 miles an hour, say 25, 30, 40, 50, even like, freeway speeds or track speeds, then this fan, if it's still on, the question is if it's still on, it's actually going to cause an impedance. It's going to act kind of like a wall, because this fan is spinning and it's pulling air at 25 miles an hour, and it's essentially blocking some of the air from naturally flowing through it, because now you have a barrier, a fan that's now spinning slower than what the air is pushing through it when the car is going like 50 miles an hour. So it's important that people understand that. And that's why a lot of times when guys in the racing world design shrouds, they do it either without shrouds, so they put just the fans on the radiators themselves without the shroud, or they make the shroud smaller, like, as you guys can see Honda did here. Or they make sure the fans turn off after a certain speed. Or actually, some guys, it's really interesting, they cut flaps here. So there's like little flaps that open and close all along the sides. They cut flaps that when the speed of the air and the pressure of the air going through it is higher than what's behind, and these flaps just open, and essentially it becomes almost like a trap door thing. I think those are pretty cool, but a little bit too complicated for me. So anyway, just keep that in mind when you're designing a high-speed fan system, that you need to take that kind of stuff into account. Okay, I didn't want to go into it too much. Oh, one more thing. A lot of guys like to put the that cover plate that goes here. I don't really fully understand why, because the factory has its own cover plate that actually does a better job of coming all the way from the bottom, which is this, all the way from the bottom and actually directly into the radiator. So, I mean, yeah, it has some, holes here and holes here, but more or less, I think it does a pretty decent job of doing that. So unless you take this out and you put an actual cover here, and you cover up some of the other holes that it doesn't go through to the side, then I can see how that would work. But again, OEM, a lot of times it's better than what we can do in the aftermarket. So what was the third thing? Water flow and the pump. So as we go back to the flow of the water, right? So going back to how a radiator works, you need the coolant, the hot coolant, to stay in the radiator long enough so that the radiator has the ability to actually pull heat out of it and transfer into the air, right? That's what it does. So it's important to know that how long the fluid stays in here and how restrictive these fins are. I'm sorry, the tubes are. You can see here the tubes are maybe just slightly bigger, but not really that much bigger than the tubes on here, but they're able to fit more tubes this way. So I believe, if I remember correctly, this actually flows more coolant than the OEM, because it just has way more tubes, but I can't remember that exactly off the top of my head. But what's important to know is that the flow of the coolant is 100% determined by your water pump in the motor. And the water pump, it's, you know, it spins as fast as your RPM. So it's very linear relationship to your RPM. So you can't really modify that. So you kind of, it is what it is. Whatever water flow you get is the water flow you're gonna have. But it's important to not have a very restrictive radiator that actually becomes the bottleneck in the water flow system. Okay, so find a radiator that doesn't do that. Whatever it is you find, you obviously, you know, you don't have to pick a MASiV or whatever, but so what else did I want to talk about here? Let's go and skip to system pressure. System pressure meaning basically boiling point, right? So boiling point's an interesting thing because at atmospheric, you know, water boils at 212 degrees. But if you increase that pressure with a racing cap like this one, this is a Type R racing cap, and this one is some other generic crappy cap that I got off some kit that I don't know, just never really used. So this one is a 1.1 bar, which I believe is about 16 pounds. If you increase the pressure in the system to 16 pounds or 1.1 bar, you actually increase the boiling point to 260 degrees. So that means that the coolant or the water in your tank will resist forming into gas much later at a much higher temperature. That's that's kind of what it means. So what was the rule of thumb? I think it's for every pound of pressure increase, you get 3 degrees of increased boiling point, something like that. And so the only thing, there's always a compromise, right? If you increase the pressure, you increase the stress in all the components of your car. So you increase the stress in your hoses, you increase the stress all along, like on the connections everywhere, all the way to the, let me see if I can open this up. You increase the pressure, most importantly, into your coolant tank. So as you notice, I use a OEM coolant tank with a Type R kind of protective UV cover. It's like a little rubber kind of condom that goes on it. But some of the things I wanted to talk about, the radiator that I'm using now, which is this one, it cools so well I no longer need to use a high pressure coolant cap. So what I do is I went back to a 1.0, which is 1 bar which I think is the factory one, is rated at 1 bar. So I don't need the boiling temperature to be that high anymore because I've never actually gotten over like 200 and maybe 205 degrees on the temperature in this car, and that was in, you know, thermal, which is in Palm Springs, basically in Palm Springs, California, running super hot temperatures. It was like 120, 130 track temps. Ambient was like, I don't know, 110 or something. So it was a really hot day, and this car was just running cool as a cucumber. It was actually pretty incredible. I normally don't like to abuse the car that way, but I actually wanted to see how the MASiV would do. So anyway, a little side note about why I use the OEM coolant tank and not a aluminum or some other metal type tank. This is just a theory that I have, and I want you guys to understand why I do this, because a lot of people have asked me about it. Obviously, your cooling system, from your radiator to the hoses all the way through to the actual pipes and everything in the car, and even like the water jackets and, you know, everything in the car, I want the weakest link in that whole system to be this, right? So if I'm going to have a leak, the leak is always going to occur at the weakest link, and I want that to be the OEM coolant tank. Why is that? Because it's the easiest to change, it's the cheapest to change. It's kind of like a fuse in the system. And that's my philosophy for wanting to use the OEM coolant tank. Not only that, but it's also baffled. So in here is a honeycomb design that keeps the slosh to a minimum. It's baffled really well. So what else did we miss here? Oh, last thing, you have to use the proper coolant that is designed for the radiator and for the components in your car. So this radiator and the components of the car obviously use it, or has been designed for the blue cap type 2 Honda 50/50 mix. So I don't use any water in here, well, aside from the 50/50 that's in there. I don't use any water wetter, although water wetter is probably going to benefit a little bit. And I basically try to keep everything as simple as possible. I try not to like overthink stuff if I don't have to. So use the proper coolant. So what did we go over here? We talked about radiator cooling capacity. So you want your radiator to be able to pull as much heat away from the coolant as possible in the most efficient way. We talked about the importance of airflow and kind of, you know, air wanting to always go to the low pressure area. And oh, one thing I didn't say in terms of airflow. So this is kind of cool. If you have a duct that's properly vented, mine isn't properly vented, but more or less it does work as an exhaust because it has nowhere else to go but here. As the speed, and I think this is like Bernoulli or something, hood's not closed, so Bernoulli's principle, as the speed of air goes and travels through this way, the faster the air travels through here, it actually creates a vacuum that wants to pull air out this way. So that gives you additional benefit in creating a low pressure area behind your radiator that pulls even more hot air out of the system. So anyway, of course you guys all knew that, right? So we talked about airflow, talked about the water flow and the pump itself. We talked about the importance of understanding the system pressure. Again, it's not a bad thing if you go with a 1.1 or even a higher pressure radiator cap, but your radiator cap is what determines your boiling point in the system. Oh, I should also say the difference between a cheap cap and a good cap. This is factory Honda. You can see that the spring, which is actually the thermostat in the system, has a lot more windings to it. There you go, has a lot more windings to it. Pardon my nails. And it's just of higher quality. Not only that, but this is like a silicone based rubber gasket, as opposed to this, a lot less windings, kind of just, you know, more or less more cheaply made rubber gaskets, which don't last as long as the silicone. So just as a note. And lastly, we talked about the proper coolant. So all right guys, that was a quick and dirty, not so quick, I don't know, maybe that was like 40 minutes. I apologize. I try to do these things faster, but there's a lot of material to go through, and I hope it's useful for you and everyone there. If you have any questions, again, I'm not an engineer, so I kind of just, you know, learned this stuff and I tested and I tried, and whatever makes sense in my head is what I put in my NSX and other cars that I've had. So hopefully that's helped. If you have any questions, then post in the comments below. All right, laters.